Okay, in this video we're going to look at a tool for manipulating generating functions to come up with new combinatorial identities. So let's just recall that given a sequence of numbers, a1, a2, up to infinity, its generating function is given by a of x, which is the sum n equals 0 to infinity, an x to the n. So in other words, the coefficients of this power series are given by this generating function. So maybe the first question we would like to ask is, what is, maybe we'll call it a sub even of x, which we could define as the sum n equals 0 to infinity of a to n x to the n. In other words, what if we want the generating function for only the even terms from this sequence? Or maybe only the odd terms from the sequence? Or maybe only the multiple of 3 terms? Or so on and so forth. So now here's what I'll notice along this path is that if we take a of negative x, we're going to get the sum n equals 0 to infinity of an minus x to the n, which is going to be the sum n equals 0 to infinity of minus 1 to the n, a sub n x to the n. Great. And notice that in this sum, the even terms have positive coefficients in front of the sequence terms, and the odd terms have negative coefficients in front of the sequence terms. So what that allows us to do is the following. So if we take a of x plus a of negative x, we can put these together. So this is going to be the sum n equals 0 to infinity of a sub n x to the n plus the sum n equals 0 to infinity minus 1 to the n, a sub n x to the n. Now mashing those sums together, we get the sum n equals 0 to infinity of 1 plus minus 1 to the n, a sub n x to the n. But now it's easy to see that this is 0 if n is odd, and it's 2 if n is even. So let's see what that gives us. That means a of x plus a of minus x is going to be equal to twice the sum of just the even terms. So a sub 2n x to the 2n. Good. So now we're almost to the formula that we want. And that is, we don't want a 2n up here, we just want an n up here, and we also don't want this coefficient 2 out front. So what we can do is divide this 2 over and then compose these generating functions with the square root of x instead of just x, and that's going to give us our final answer for this a even. So what I'll do is I'll clean up the board and then we'll present that final answer. Okay, so we did some calculations on the last board, and those calculations quickly follow us to be able to write that the sum n equals 0 to infinity of a sub 2n x to the n, which we called a sub even x, is actually just 1/2 times the quantity a evaluated at the square root of x plus a evaluated at negative square root of x. Which may not seem super helpful, but often we have a closed form for these generating functions, and so we can simplify that closed form, and we'll see that in an example later. Now you might also ask, well, what about the odd terms? And so we could have the sum n equals 0 to infinity of a sub 2n plus 1 x to the n, so we could maybe call that a odd of x. And that's very, very similar. So that's going to give us 1 over 2 times the square root of x, a root x minus a negative root x. So notice we need this extra square root of x in here. So let's go ahead and check that that makes sense. So this is going to be 1 over 2 root x. And now we have the sum n equals 0 to infinity of a n x to the n over 2. So that's the first part. And then minus the sum n equals 0 to infinity of minus 1 to the n a sub n x to the n over 2. Great. So that's what we get by composing negative the square root of x in there. Good. So now what we'll notice is that we can put these two together. So we have 1 over 2 root x, and then the sum n equals 0 to infinity of a sub of 1 minus negative 1 to the n a sub n x to the n over 2. But now notice this term right here is 0 if n is even and 2 if n is odd. So that means all we get is the odd terms. And if you stick an odd term in this n, notice that you'll get an extra square root of x, which will cancel this thing in the bottom. So let's do all the details here. So this is 1 over 2 root x, and then the sum n equals 0 to infinity of a sub 2n plus 1, because only we have the odd terms left, and then x to the 2n plus 1 over 2, so that's going to be the same thing as x to the n plus 1/2. So let's reiterate, 2n plus 1 over 2 will be n plus 1/2. Great, but now this half will cancel the square root over here, and I should say we had a 2 out here. So that 2 cancels that 2. Good. And then the square root of x cancels this half, and we're left with exactly what we want. Okay, so I'm going to clean up the board, and then we're going to look at, well, what if we want a 3 here instead of a 2? Okay, so now we want to look at, well, what if we want a generating function for the multiples of 3, and we need a little bit of the theory of the roots of unity in order to do that. So let's let eta equal e to the 2 pi I over 3. So notice this is a root of z cubed minus 1, which can be written as z minus 1 times z squared plus z plus 1. Great. And in fact, we know that this is not equal to 1, which means it's not a root of this part, so that means it has to be a root of this portion of that factoring. So in other words, we have this formula, eta squared plus eta plus 1 equals 0. Great. So now we're going to use that same theory that we used before to construct a generating function with only the multiple of 3 terms. So let's look at the following calculation, which will do that. We'll take a of x, actually let's do maybe a of x to the 3rd plus a of eta x to the 3rd plus a of eta squared x to the 3rd. Now, notice that's going to be the sum n equals 0 to infinity of a sub n x to the n over 3. So that's this first term, plus the sum n equals 0 to infinity of eta to the n a sub n x to the n over 3. And then finally, the sum n equals 0 to infinity of eta to the 2n a sub n x to the n over 3. Okay, good. So now we can put all of these together. So that's going to be the sum n equals 0 to infinity of 1 plus eta to the n plus eta to the 2n times a sub n times x to the n over 3. Now the next thing that we want to notice is if 3 divides n, then 1 plus eta to the n plus eta to the 2n equals 3. Okay, so let's look at the details of this. So if 3 divides n, that means n equals 3 times k. And now notice that eta to the n in that case is really equal to eta cubed all to the k power using exponent rules. But the fact that eta is a root of that polynomial, we know that eta cubed is actually equal to 1. So that makes this equal to 1. And likewise, eta to the 2n is really just eta cubed to the 2k, which is also going to be equal to 1. So that means we get a 3 right here. Okay, so I'm going to erase this part, and then we'll look at, well, what if 3 does not divide n? Okay, so now we'll look at the case when 3 does not divide n. There are actually 2 cases here. We'll only do one. What if n equals 3k plus 1? And the other case would be n equals 3k plus 2. So let's see what we've got here. So that means eta to the n is equal to eta to the 3k times eta to the first power. But eta to the 3k is equal to just eta. Great. But now that means eta to the 2n is equal to eta to the 6k times eta squared. But now that's going to be just eta squared. Good. But what that's going to tell us is that 1 plus eta to the n plus eta to the 2n is the same thing as 1 plus eta squared, which is equal to 0, given that it's a root of that orange boxed polynomial. Okay, good. And then similarly, if n is equal to 3k plus 2, we get the same kind of setup. So what we end up with is a 2 here, a 2 here, and a 1 here, and a 1 here. And I think we have this is like plus 3 or something. Okay, good. So I'm going to clean up the board, and then we'll take it home for a formula for every third term in a sequence. Okay, so on the last board we came up with the following equation. So we have a of x to the third plus a of eta x to the third plus a of eta squared x to the third is equal to the sum 1 plus eta to the n plus eta to the 2n times a of n equal, x to the n over 3. And then also we saw that this was equal to 3 if n was equal to 3k, and it was equal to 0 if n was equal to 3k plus 1 or 3k plus 2. Good. So what that allows us to do is simplify this down to the sum n equals 0 to infinity and only keep the multiples of 3. So in other words, we could have, this is a 3 that comes out front, a sub 3n of x to the n. Now notice that allows us to solve for a sub 3, which maybe we could define as the sum n equals 0 to infinity of a sub n a sub 3n x to the n. So this is going to be 1/3 times a x to the third plus a eta x to the third plus a eta squared x to the third. Like that. Okay, good. So now that we've got a feel for how to do these things, I'm going to clean up the board and then we're going to look at an example. Okay, so I want to do an example involving the Fibonacci numbers because I think they're nice. So let's recall that we have f sub 0 is 0, f sub 1 is 1, and then f sub n is defined by this standard two-step recursion. So it's n minus 1 plus f sub n minus 2, and that's for n bigger than or equal to 2. And in a previous video, we calculated the generating function for the Fibonacci numbers, and we found that that was x over 1 minus x squared. So I won't rederive that here. So now we want to look at f sub 3 of x. So in other words, that's going to be the generating function for every third Fibonacci number. So we have f sub 3n x to the n. And then by our calculation that we did in general on the last board, so that should be 1/3 fx to the third plus f eta x to the third plus f eta squared x to the third. Okay, good. So now composing that into the generating function, which is known, we get that this is 1/3 times the quantity x to the third over 1 minus x to the third minus x to the 2/3 plus eta x to the third over 1 minus eta x to the third minus eta squared x to the 2/3 plus eta squared x to the third over 1 minus eta squared x to the third minus eta to the 4th power, but notice eta to the 4th power is eta cubed times eta. We know eta cubed is 1, so that's just going to be eta x to the 2/3. Great. So now the next thing that we need to do is find a common denominator, and the common denominator will be just the product of all of these denominators. So let's calculate that real quick. So calculating a common denominator, we're just going to take the product of all of these. So 1 minus x to the third minus x to the 2/3, 1 minus eta x to the third minus eta squared x to the 2/3, 1 minus eta squared x to the third minus eta x to the 2/3. Good. Okay, so let's see what we get when we multiply that out. So let's first of all look at the constant term. So the constant term is just going to be 1 times 1 times 1. So we get 1 for the constant term. Now the next thing I want to look at is what do we get for the x to the 1/3 term. So if we look at the x to the 1/3 term, we're going to get a -1 from this. So that'll be -1 there. We'll get a negative eta from that, minus eta. And then we're going to get a minus eta squared from that guy over there. So we get a minus eta squared for that. So, but we know that this adds up to 0 by the fact that it's a root of that polynomial that we had on the board before. So this is going to become 0. Great. So the next thing we want to do is look at the x to the 2/3 coefficient. Great. And we're going to get that from 2 different places. We're going to get it from just these x to the 2/3, which are part of all of these, and then multiplying x to the third with x to the third. So let's be careful about that. So notice we'll get them from this, like I said. Good. So that's, again, going to be -1 minus eta squared. Great. And then we also get them from multiplying these guys out, from taking 2 of these things that are yellow circled and then the 1 as the next. Great. So let's see what we get from that. So from this and this, we get a minus eta. Good. From taking this one and this one, we get a minus eta squared. Okay. And then finally, from taking this one and this one, we get a minus eta cubed, which is a -1. Good. But now notice that both of these terms are 0, just as before. Okay. Fantastic. Now let's look at the x term. So the x to the 1st power term. So great. Now that's going to come a couple of different ways as well. We can get it from multiplying an x to the 3rd to an x to the 2/3, or we can get it by multiplying all of the x to the 3rds. So let's first get it by multiplying all of the x to the 3rds. But notice if we do that, we have x to the 3rd negative eta x to the 3rd, negative eta squared x to the 3rd. So that's going to be an overall eta cubed x to the 3/3, in other words, x. So that's going to give us a -1. Okay, so we'll also get it from multiplying the x to the third with x to the 2/3. So we've got several ways that's going to happen. We could take this x to the third and those two x to the 2/3. So let's do that first. So taking this x to the third, we'll get this eta squared. So it's plus eta squared plus eta. And those are pluses because everything has a minus sign. Good. Now the next way we can do it is taking this x to the third and then the two flanking x to the 2/3. So again, that's going to give us plus eta and then plus eta squared. Great. So another plus eta squared. Okay. Fantastic. And now one more, we could take this x to the third and then these two x to the 2/3, and we're also going to get a plus eta squared. Great. But now what we can use here is the fact that all of these add up to -1 by the fact that if we recall, eta squared plus eta plus 1 was equal to 0, which means eta squared plus eta equals -1. So we have -1, -1, -1, -1. So all of this right here is -4. Okay, good. So I'm not going to do the rest of the calculation, but it really just involves foiling everything out super carefully and noticing these kind of things with these roots. I'll just skip to the end. Okay, so skipping to the end, we have the product of all of these denominators is 1 minus 4x minus x squared. So we notice this 1 and this -4, and I'll leave it to you to fill in all of the rest of the details. Okay, good. So now, once we have this common denominator, it's fairly simple, although a little bit tedious, to simplify out this big term, but it's really not that bad. So let's just skip to this thing being calculated out. So I want to reiterate what you would need to do is put this common denominator in all of those rational functions. So multiply this whole term by those two denominators multiplied over themselves, and so on and so forth. So skipping to the generating function, for this up here, we have the following. Okay, good. So skipping to that generating function, we have 2x over 1 minus 4x minus x squared. So again, it's just fairly elementary but tedious. Okay, good. So now we have this is equal to this, which allows us to come up with some nice combinatorial identities pretty easily. For instance, let's do the sum n equals 0 to infinity of f sub 3n over 10 to the n. And I will say one thing, you have to be careful about the radius of convergence of this. I'll let you guys think about how to calculate the radius of convergence for this kind of thing. It's not too bad in the end, but you do have to worry about that. So notice that this generating function evaluated at 1 over 10, so that is within the radius of convergence. So notice that's going to give us 2 over 10, which is 1 over 5, over 1 minus 4 over 10, which is 2 over 5, minus 1 over 10 squared, so that's going to be minus 1 over 100. So you get something like that, but then doing the elementary arithmetic, this ends up being 20 over 59. So we've got this nice combinatorial identity involving Fibonacci numbers that we got through this nice new strategy. Okay, this is a nice place to end the video.